We're dealing with the knowledge area, electricity and magnetism. Our topic for today is current electricity. Let's look at electric circuits. So when a circuit is complete, current can move in a circuit. And current can be a flow of positive charges, which we call conventional current, or negative charges, which we call electron current. A conventional current is direction from positive to negative terminal of a battery. An electron current, the direction is from negative to positive terminal of the battery. We are going to be using conventional current. That means the direction is from the positive terminal to the negative terminal of the battery. Now, in a copper wire, as you know, we have delocalized electrons, and that we know is elicited from our model of metals, which has to do with metallic bonding. Alright? So we need a battery to provide an electric field that pushes the electrons in a wire and do work on a component. Now what you need to remember is that if you buy a hose pipe or a hose, you don't get the water with it. Am I right? But if you buy an electrical wire, you get the electrons with it. And we know in an electrical wire, and if it's a metal and it's a conductor, the electrons are delocalized. Right. So all you need is something to push the electrons. And the apparatus that can push the electrons could be batteries, or it could be magnets, or any other way in which electrons can be pushed. Now, let's look at a circuit. In order for current to flow, you must have a closed, the circuit has to be closed for current to flow. Here in this situation, you have your battery. You've got your bulb here, and you've got the switch, right? But current does not flow basically because the circuit is not complete, it's not closed, right? So for current to flow, you need to have a closed circuit. Let me demonstrate that. Here we have, let's say, a battery, and we have a copper wire, and let's put a switch here, and let's have another copper wire there. Let's put a switch here. Alright, let's put a bulb there. Copper wire. And let's have a copper wire here. Right, and let's just have that. Have another switch here, another bulb here. Let's connect that, right? And let's connect it there, right? So we can see there's no current flowing through the circuit. So let's say, for instance, I close this particular switch. We still don't have current in the circuit because, as you can see, the two switches are open, so there isn't a complete pathway for current to flow, right? So if I now close one switch, I see the bulb burns. That means I've got a complete circuit and the electrons can flow. Here I'm showing you electron flow, but we're going to use the conventional direction, so let me change that. Right, so there it goes from the positive, and as you can see what's happening to the charges in your filament. It goes through your filament and then it goes to the other side of the battery. The bottom bulb is not burning because that particular circuit is not complete, so it's not closed. So in order to close it, I will then close that switch and see there's the circuit is complete and the bulb burns. If I now open the switch on top, find that current cannot flow because the circuit is not complete, right? And if I close it, there we have. Electron current moves in the opposite direction. Right, so let's say if we want to just have the components here in terms of the symbols, I could just do that, and here it gives you an idea. You've got your cell and you've got your two bulbs. Right, so there you have that, and that gave you an indication of your current moving through the circuit, and when your switches were closed, you found that the bulb burned, right? So if we now go to the components, if we look at the connecting leads, they're given by that. The cell, one cell is shown, and here you've got two cells. So now for the cell and the battery, you could just have one cell, and that's fine. Here we have a resistor, but the resistor can also be shown like that. I prefer showing a resistor like that. And then we have our filament, lamp, and our voltmeter, and we have our ammeter. Ammeter measures current, voltmeter measures the voltage. That means the force with which the current moves past two given points, and then we have a switch. So the voltmeter actually measures the change in potential energy per unit charge between 2 points, but we'll get to that. So here I have a circuit, and I have a bulb, which we have that, and then from there to there we have our switch, and then we have our resistor like that, and then we have our ammeter, and then right, that's our ammeter, and across this resistor we have a voltmeter, right? And the voltmeter is connected in parallel, right? We'll talk more about that a bit later in the lesson. And then the ammeter is connected in series. What do I mean by that? So we said we're going to use conventional current. That is our positive. That's our negative. So current moves in that direction. So the ammeter is connected in series. That means there is only one conducting path, and the electrons or the charges move through this ammeter, and then it comes, the charges then move through this particular resistor here, and the voltmeter is connected in parallel because it actually measures the voltage between these 2 points. Let's call them A and B, right? And it measures the voltage between the 2 points, and here your bulb is also connected in series, right? So your voltmeter has to be connected in parallel, and a voltmeter has a very high resistance, right? We'll talk about resistance later. And an ammeter has got a very low resistance, right? Okay, so you cannot put a voltmeter in a circuit in series, right? You cannot put a voltmeter here. A voltmeter has to be connected parallel to a particular component, right? Okay. Now, let's look at models of electric fields and the electric potential energy associated with system of charges. Let us examine potential energy changes, right, associated with the configuration of charges in an electric field. Now, we cannot talk meaningfully about difference in voltages or potential difference, electric potential or electric potential energy without having at least a qualitative understanding of an electric field. So we know what an electric field is. We know electric field is a region in space where a charge experiences a force. And the concept of potential energy or stored energy is useful in the study of electricity. The concept of electric potential is defined as the amount of energy per charge at a particular position, and whereas voltage is the difference in electrical potential at different positions. Right. So, voltage and electric potential are key conceptual components in understanding circuits, and both are measured in volts. Right, now let's look at electric fields. The reason we're looking at it so that concepts that are related to it, makes more sense. And when we talk of potential difference or electric potential, then at least we can relate it to some sort of mental model that we have. Okay. So, if we look at the electric field of a positive charge, okay, and here we have the positive charge, right? Let's look at the field. Right, if you look at the field, here you will see that you have a positive charge here, and the field moves from that positive charge outwards. If we look at a test charge, right, a test charge is a very tiny charge which we bring into the vicinity of the electric field of a positive charge. Now, if we have a positive charge or test charge in the vicinity of this electric field, you will see that it moves in the direction of the field. It would move in a direction from A to B. Right. So it moves in the direction of the field. Then, if, for instance, we bring the test charge closer to the charge in the center, or when we move it from B to A, what happens is that the potential energy of this particular system increases. Right. So we can look at these two charges as forming a particular system. Right. So what happens is when the charge moves from B to A, the potential energy increases. When the positive charge, moves in the direction of the field, the potential energy decreases. If we, for instance, have a negative charge, right, and the negative charge is near the positive charge, right, and if the negative charge will move in the direction of opposite direction of the field, and when it moves in the opposite direction of the field, we find that the potential energy of this system decreases. Right. And if the negative charge moves further from the positive charge, we find that the potential energy of the system increases. Right. Now, let's go back and have a look at this. So, the natural direction or movement of charge, if it's a positive test charge, it moves in the direction of the field, and in doing so, the potential energy of the system decreases. If we have a negative charge or test charge, and this moves in the opposite direction to the field, right, and if it's moving in the opposite direction to the field, what happens? The potential energy also decreases. Alright. Now, let's look at the work done. The work done on a charge by an external field. So when a positive charge is moved opposite to the electric field, the potential energy of the system increases. When a negative charge is moved in the direction of the electric field, right, the potential energy of the system increases. And then we have electric potential. Electric potential of a positive test charge is high near a positive charge, and the electric potential of a positive test charge is lower from a positive charge. When it's further than it's from a positive charge. Okay, so there the electric potential is lower. Okay, so now if we look at this here, and we look at this, and let's say for instance I have Q, right, positive, and let's say we fix it. Say Q is fixed. Right? So let's say Q is fixed, and it's fixed here. Okay, so Q is fixed, right, and let's say we've got a charge Q plus, right, and this charge Q plus is moving in the direction of the field, right. What happens is the potential energy, or I'll just write it as potential energy decreases. Right? If I have a charge Q, also plus there, right, we find that, and if this is moved towards Q, we find that potential energy increases. If I have a charge Q negative, right, and it is moved towards the positive charge, we find that EP decreases. And if we have a charge which moves further away, EP increases. Right, so let's look at maybe the work done in each case. Say the work done when the charge moves from, when the charge Q moves away from the fixed charge. What happens in that case? We find that the field does the work. When we find that the charge is moving towards the fixed charge, there has to be an external force that's moving the charge. Okay? External force. And when the negative charge moves, so the work is done by the field, the electric field. And then when the negative charge is moved away from the positive charge, then the work is done by an external field. External field. Something that's moving or separating the charge. And normally for us, what does that is in a battery. A battery can be used to separate the charges, right? And what helps do that is the chemical reactions that take place in a battery. Right, now let's look at the electric field of an oppositely charged parallel plate. Okay, here we have a parallel plate. You're not going to be examined on the pattern of these fields, but I'm just using it to illustrate the idea of potential energy, electrical potential energy. Right, so here we have a parallel plate that has a field, and the field is from positive to negative. You got a positive plate and a negative plate. As you can see, here you have got a positive charge and it's near a positive plate, so it has a high potential energy, right? And here it's at a negative plate, so it has a low potential energy. And by definition, when the positive charge is near the positive plate, we say it has a high potential or a high electrical potential. And when the positive charge is near the negative plate, we say it has a low electrical potential. Now, it's the same thing again. When you have a negative charge near a negative plate, here it's going to have a high potential energy, right? When it moves and it's here and the positive, then it's going to have a low potential energy, right? Low potential energy. But it still has a low electrical potential, and here at the positive plate it's going to have a high electrical potential, right? And if your charge, positive charge, moves from A to B, that means the field is actually doing the work. If your positive charge moves from B to A, that means something has to move it to A, so an external force does the work on it, right? And in that case, some instrument or apparatus has to be used in order to push those two positive particles together. So here we have that. The natural direction, right? And I'm only looking at potential energy. I'm not looking at the kinetic energies. So a positive charge tends to move in the direction of an electric field from A to B, and it decreases the potential energy. A negative charge moves in the opposite direction from B to A, and it decreases the potential energy. Right, the work done. An external force is applied to move it from B to A, right? And in doing so, it increases the potential energy. And also an external force moves a negative charge from A to B, increases the potential energy, right? So you need to look at that carefully and look at and relate it to that field. And then an electric potential plus Q at A is high and at B it's low by definition. So we have our again a negative charge at A is high and at B it is low, right? So generally charges naturally move in a direction that lowers their potential energy. Okay. Right, now let's look at energy transfers. If we look at energy transfers from a battery to a system, right, so we're looking at the energy transfer from a battery to a component, and let's say the component is a system. And what happens is the battery is now transferring energy to a component. The component could be a resistor, the component could be a bulb, the component could be some instrument or load that is connected to a battery, right? The potential difference across a component can be used as a measure of the potential energy transferred per unit charge to the component by the battery, right? So potential energy from the battery gets transferred to the component. The battery does work on the component, and in doing so it increases the energy of that particular component, but in the process the potential energy or the store of energy of the battery decreases. So the battery supplies the energy to the component, and the component's energy increases, right, of that system, but the battery energy decreases. So what happens inside the battery? Chemical reactions in the battery will have to work harder to replenish the store of energy in the battery. Now what we need to realize is that a battery is a potential energy supplier. It doesn't supply electrons. All it does, it supplies potential energy and the electric field in order for those charges to move. So electric field is a useful model and gives us qualitatively relative position in the field, right, can be illustrated. So the greater the potential difference across or drop across a component, right, the bigger the amount of energy being transferred to the component. And the negative terminal of the battery is generally assigned a zero potential or a zero electric potential and is considered to be a reference. Right, now let's try and decode some of that. So let's say we have a cell, and let's say we have a 12 volt battery or a cell. So here we have, say, a circuit, and we have our resistor, and there we have a circuit that's complete, and I haven't put a switch there, right? So there's 12 volts. Right, now in here we know that's our positive and that's our negative, and the positive pole here has got a high potential energy. The negative pole here has a low potential energy, right? And we're having positive particles moving. We're using conventional current. So the current goes there, like that, and like that. And then we find that if we have a voltmeter here, the voltmeter can measure the push, and if we have one component here, there's always a potential drop whenever you have a resistor or a load, and here the potential drop would be 4 volts, right? And here we have our current moving through here, and the battery transfers its energy, let's say between A and B, transfers its energy between A and B, and so energy is transferred by battery to the component. In this case, we've got a resistor, and it could be a kettle. So when energy is transferred to this resistor by the battery, and if it's a kettle, it can boil water. If it's a fan, we can get mechanical energy. If it's a light bulb, we can get light. So what happens is then energy gets transferred to this particular resistor, and the energy comes from the battery. So the energy in this component or the system here increases, and then we have either light or heat, but the battery in itself loses energy, right? It loses energy, and as it loses energy, what happens is the chemical reactions in the battery have to then work harder, and then chemical potential energy gets transformed to electrical potential energy, so it replenishes the store of charge in the battery, right? And if we, for instance, look at the resistor, you have your potential drop at this resistor. So remember that, say for instance, if I look at this point here and this point there, and I have a voltmeter connected between these 2 points, this voltmeter is going to read 0. Why? There's no load, it's a conductor, and in this conductor here, you don't have a potential difference between 2 points, only between your a resistor here, there's a potential drop. And because the battery is 12 volts, we find that the potential drop across that resistor is 12 volts. If I had 14 volts or 20 volts, then the potential difference would be 14 or 20 across this particular resistor. And also, if we say the potential energy of at the positive terminal is greater than that at the negative terminal. Also, we could say, so thus our electric potential here would be 12 volts, and our electric potential at the negative terminal could be 0 volts, because we use it as a reference, right? So the difference between the negative and positive terminal, the voltage is 12 volts. Right. Right, the potential difference. The potential difference between 2 points is defined as a change in potential energy of a charge moved from A to B divided by the size of that charge, right? Alternatively, the work done per unit charge is known as potential difference, right? So here we got V is equal to W upon Q. So V, the potential difference, is given by W upon Q, right? The unit of work is joules. The unit of charge is a coulomb. So a joule per coulomb is a volt, right? And the physical quantity potential difference, right, is given by V, and the symbol for it is volt. Charge is measured in coulombs, and work is measured in joules. Alright, now measuring the EMF and potential difference. A voltmeter can be used to measure potential difference across a battery or a component. And it gives us an indication of the electric potential energy per unit charge. Now, the voltage of a battery in a circuit when the switch is open gives the EMF of the battery. The voltage of the battery when the switch is closed gives us an indication of the potential difference of the battery. Now if we look at this, let's say for instance we have that, and we have here we have a switch, like that. And if we measure the voltage across the battery, with the switch open, we measure the EMF of the battery. Right? That means when the switch is open, there's no current in the external circuit, and if our voltmeter has quite a high resistance, we measure the EMF of the battery. But if the switch is closed, then we measure the potential difference of the battery. And in this case, there's a current that moves in a external circuit. Okay. So in a battery you normally have an internal resistance, and what happens is when a current flows, then there's a certain amount of volts that is lost within the battery, or which is there's a voltage drop within the battery, and then and if we then measure the voltage, you actually measuring the potential difference rather than the EMF, because current then flows in the external circuit. And why does a battery get flat? A battery, as we know, transforms potential energy into electrical potential energy, right? If the reactants are used up, then this used up chemical potential energy cannot be transformed into electrical potential energy. So then the battery is flat. Let's look at the schematic representation of a voltage drop across bulbs in circuit A and circuit B. So let's say, for instance, here you got circuit A, and this particular battery has a voltage of 1.5 volts, and you got a bulb across there. So if we look at this schematically, we have that, and we have a bulb there like that, and if we have a voltmeter here to measure the voltage, we find that, and if this is 1,5 volts, right, we find that here the voltmeter will also read 1,5 volts. That means there's a potential drop across our bulb of 1,5 volts, right? Then whenever there's a resistor or a load, a voltage drops across that particular load. So you find that here we have our battery, which is has a voltage of 1.5 volts from A to D, and then we say here from B to C there's a drop of 1.5 volts, right? So let's look at the next one. Here we have this, and there's two bulbs, so each one there will be a potential drop, which means we have that, and if we have this here, there's a bulb, and there we have another bulb, okay, and here if we have a voltmeter there, right, and a voltmeter here. So you're going to have a potential drop. So here you got 6.5 volts. I beg your pardon. 6 volts. 6 volts, and that means if these two bulbs have equal resistance, then you would have 3 volts being dropped at each bulb. But then, as you can see here, if that is, say, B, and that is C, and this is D, and that is E, right? So you got your voltage by a battery which is 6 volts, right? And a certain voltage drops here and a certain voltage drops there, and which is then equal to the total voltage of the cell. Right, now let's look at here. We have 120 joules of work is done in lighting a bulb, right? And a charge of 20 coulombs flows through it. What will be the potential difference be across the bulb? So we have, for instance, a battery there, and here we have a bulb, okay, and we have current moving like that, and the amount of charge that moves through here is 20 coulombs, and the amount of work done by the battery is 120 joules, right? So 120 joules of energy is transferred to this particular bulb. We want to know what is the potential difference across this bulb, so which then means V is equal to W upon Q, right, which is 120 joules upon 20 coulombs that passes through that, which gives us 6 joules per coulomb, which is then equal to 6 volts. So that means the voltage across this would be 6 volts. So if I had to put a voltmeter here across there like that, that would measure, if I had a voltage there, it would measure 6 volts. Right, now here we have how much energy is transferred when 60 volt source allows 6 coulombs of charge to flow through a conductor. Right, so W is equal to VQ, okay, and which means you got 60 volts times 6 coulombs, which gives us 360 volts coulomb, right, which is equal to 360, and a volt is joules per coulomb times a coulomb, which gives us 360 joules. I have a coulomb cancels out. Right, now let's look at the definition of a current. Current is the rate at which charges move past a given point in a circuit. Right? The unit of current is the ampere, which is defined as a coulomb per second. Which is that? Coulomb per second. The ampere is now linked to a natural constant. That means it is linked to the electron. Most of your SI base units have been redefined in terms of natural constants now. Right? So the SI unit of electrical current, it is now defined taking a fixed numerical value of the elementary charge, which is the charge on an electron, and when this charge is expressed in coulombs, and the coulomb, which is equal to ampere second, right? And where the second is actually defined in terms of the frequency of a cesium atom. As you see there, right, the unit coulomb, which is actually amp second, right? So if you got Q is equal to I T, current is measured in amperes and time is measured in seconds, therefore coulomb is an ampere second. Right, so if you look at current, it's measured in amperes, right? And like I said there, ampere is equal to coulomb per second. So let's look at this here. If we have, for instance, this, and here we have an ammeter, right? And we have and let's take that. Let's do that. Maybe it'll be better. Alright, so we got this, and we got our ammeter here, and we got our switch, and we have our resistor there, and we have our ammeter again. Just illustrating that our ammeters are connected in series, right? Again here it's connected in series, right? And then our current moves from positive to negative, and we know that the ammeter has to be connected in series because the current moving through that path is measured by the ammeter. So ammeters have to be connected in series, and ammeters have very low resistance as compared to voltmeters. Voltmeters have very high resistance. So it's because they do not actually measure the current, they measure the potential difference between components, right? And so we cannot, if I do this, that would be incorrect, because you cannot connect an ammeter in parallel, right? The ammeter has to be in series. So we can't have that, right? We could have a voltmeter here to measure the voltage across that particular component. Alright, now let's look at the amount of charge equal to 50 coulombs that passes a given point in 1 second. What is the current in the circuit? So if we want to know the current in the circuit, we say I is equal to Q upon T, which is equal to 50 coulombs upon 15 second, 1 second, which gives us 50, which gives us 50 amps. And here the amount of charge that passes a fixed point in 3 seconds, right? What is the current? So I is equal to Q upon T, which is equal to 150 coulombs divided by the time that it takes to move through, right, 3 seconds, which is then equal to 33, right? This is 159 coulombs in 3 seconds, which gives us 33 coulombs, right, per second. I'll just do that properly. That is 150. That's 159 coulombs in 3 seconds, which gives us 33 coulombs per second, which is then equal to 33 amps. Right, now we have, say, 100 electrons that move past a given point in 0,1 seconds. What is the current in the circuit? We know 1 electron has a charge of 1.6 times 10 to the minus 19 coulombs. Therefore, 100 electrons will be 100 times 1.6 times 10 to the minus 19 coulombs, right? Which would then be equal to, 1.6 times 10 to the minus 17 coulombs, right? And that, if we want to now know the current, I is equal to Q upon T, and which is equal to 1.6 times 10 to the minus 17 coulombs, all upon 1 times 10 to the minus 1 second, which gives us 1.6 times 10 to the minus 16 amps. Okay. Right, now we have here a 15 coulomb of charge flows through a filament, right, of a light bulb in 2 seconds. What is the strength of the current? So I is equal to Q upon T, which would be equal to, which is equal to, which is equal to 15 coulombs upon 2 seconds, which is then equal to 7.5 amps. Right. Okay, now we have the current strength in a circle, in a certain part of the circuit is 7.5 amps. How much charge passes through the circuit in 5 hours? So Q is equal to I times T, right? And which is equal to 7.5 amps times 5 hours. So 5, to bring it to minutes, you multiply by 60. To bring it to seconds, you multiply by another 60, right? Which will then be 135,000 coulombs, right? Okay, that gives us that. Right, now we want to know how long it takes a charge of 50 coulombs to flow through a circuit, right, which has a strength of 2 amps. So I is equal to Q upon T, which means it is 50 coulombs all upon 2 amps, which then is equal to 50 coulombs, right? And 2 amps is the same as 2, which is the same as 2 coulombs per second, where amp is equal to coulomb per second, since we say amp is equal to coulomb per second, or is the same as saying coulomb per second, and which means coulomb cancels out here, and we have 25 seconds. Okay, there we done. That's all for today. See you next time.